session, Professor V.T. Sharma is presently a visiting professor at IIT Gandhinagar, emeritus fellow at IIT Mumbai. His legendary work experience includes former head Department of Mathematics, IIT Bombay, visiting professor at IIT Goa, institute chair professor at IIT Bombay, with nearly 100 research publications. His research interest in the field of quasi-linear system of partial differential equations, non-linear gas dynamic and shallow water waves, Lie groups invariance for solutions of partial differential equations, etc. Besides his association with many prestigious academic committees, he is a member of NCM Committee for TEW, for which one workshop is being conducted here. Long list of his awards. I will just mention a few. He is recipient of President of India Award for Best Research Paper Presentation, Excellence in Teaching Award, IIT Bombay, M.N. Saha Award for Research Work in Theoretical Sciences from UGC Government of India, Professor S.T. Bhattacharya Research Excellence Award in Pure Sciences, Distinguished Services Award for his outstanding contribution to promote applications of mathematics in India, Research Dissemination Award. There are many more, but time constraint is there, so I will just put a stop over here for his achievements. And one thing I would like to mention, that during his IIT, one of his students has written in his blog, and he has given a credit to him as another god at IIT, which is always close to my heart, that he is so worshipped among his students. So now over to you, sir. Hope you will have a very enriching time with Professor V.T. Sharma. Over to you, sir.
Thanks a lot for this kind introduction. So, all right. So in this talk, I will start with first order partial differential equations. First order PDEs.
But click on this full screen mode.
Yes, I will do that. I will do that.
Yes, sir.
Now it's okay.
So I'm sure that by the way, how many participants are there? And can you just tell me the number?
So 75.
Okay, all right. So you see, the first order partial differential equations, in fact, they appear in a large number of physical processes. It is well known that most of the physical phenomena, in fact, are modeled by partial differential equations. If it is higher order, it can be expressed as a system of first order partial differential equations. So in fact, a large number of physical phenomena are modeled by partial differential equations under the assumption that the variables which describe the state of a physical system are sufficiently smooth. Right? This is the assumption. For example, if suppose U is the unknown function and it depends on the variables, say x and y, then it is assumed that dy u, dy x, dy u, dy y, etc. I mean, these derivatives exist, not only they exist, but they are continuous as well. So I again repeat, these first order partial differential equations appear in a large number of physical processes, right, under this assumption. But there are physical processes where this is not true. I mean, the system, in fact, breaks down after a finite time or a finite running length. No matter how smooth is the initial profile, right, your solution breaks down after a finite time or a finite, that we will talk about it, you see, a little later. But this is fact of the matter that this breakdown takes place. So anyway, here we shall be dealing with a differential equation of this kind, f of x, y, u, ux, uy equal to 0. Here, u is the unknown function, x and y are the independent variables, ux and uy, right? These are the first partial derivatives with respect to x and y respectively. Okay, so perhaps you may recall that in an ordinary differential equation, if you are required to find the integrating factor, what do? If the differential equation is of the form, say, mxy, plus nxy y dash equal to 0. And if you are, yes, required to find the integrating factor, what we do? We multiply it by mu, and then, yes, it reduces it to a partial differential equation. So in fact, this ordinary differential equation reduces to a partial differential equation. Here mu is the integrating factor. I multiply this differential equation by mu, right? Mu, which is a function of x and y, then it takes the form n mu x minus n mu y. This is equal to mu times my minus nx. Perhaps you may recall that now from here we get this result that under what condition, if 1 upon m minus n mu is a function of x alone or mu is a function of y alone, then we get some, right? Easily some integrating factors of a given differential equation. But you see, if you look at it, this is a first order partial differential equation. Similarly, if the function f is an analytic function, right? F is an analytic function of z having this real and imaginary parts. We know that real and imaginary parts, they are the solutions of the Laplace equation, right? So these, we know that I just mentioned that higher order partial differential equations can be expressed as a system of first order. This we will discuss it a little later. So next we come to classification. This is important. So you see, a differential equation which is of the form a x y u. A depends, this coefficient depends on x, y, and u. X and y are the independent variables, and u is the unknown function. This ux plus b, which is a function of x, y, u, uy, this is equal to c, which is a function of x, y, and u. Right? This is called quasi-linear. This is called quasi-linear. Right? If the partial differential equation can be written in this form, we call it quasi-linear. We call it quasi-linear. Why it is called quasi-linear? Because it is linear in the highest order derivatives, right? It is linear in the highest order derivatives, but it is non-linear in u. U appears in this coefficient as well as it is ux. So it is non-linear in u, but linear in the highest order derivative. Such a differential equation is referred to as quasi-linear, right? If these coefficients, if the equation is of this form, a which depends only on x and y, b depends on x and y only, and c is a function of x, y, and u. This differential equation is referred to as semi-linear. So what is the definition? In a quasi-linear partial differential equation, highest order derivatives, they appear linearly. Similarly, in a quasi-linear partial differential equation, right? In a quasi-linear partial differential equation, the coefficients, they appear, they are the functions of u. They may be functions of u, and say, so had it been uxx, then yes, possibly it could have been a function of ux also. Means the coefficient functions cannot be, these coefficients, a, b, etc., they cannot be functions of ux and uy, right? That is, the coefficients, they depend on u if the highest order derivative is 1, right? If the highest order derivative is 2, then they may depend on u and ux both. So the classification says a partial differential equation is said to be quasi-linear if the coefficients of the highest order derivative terms, right? Here it is ux, uy, so it depends only on u, right? X, y, and u. Semi-linear. A differential equation is said to be semi-linear if the coefficients of the highest order derivative terms, they neither involve u nor its derivatives. They are functions of x and y only. The right-hand side is a function. So you see, this is non-linear, but a very special class of non-linear. But of course, this semi-linear is embedded in the class of quasi-linear partial differential equations. Now, similarly, what we say that is linear, if it is of the form xy, uy, and it is of the form, say, C1, which is a function of xy u plus C2, which is a function of x and y. If the different, again, it's a very special case of this, when the function C is linear. C is linear in U. So the classification is like this: quasi-linear, semi-linear, and linear. So we will talk about the nature of the solutions when it is linear, right? What is the difference when it becomes semi-linear, and what happens when it is quasi-linear? So this is, we are going to discuss in this lecture. All right. So I think this classification is clear to you people, but maybe that perhaps some further examples would be necessary. For example, if I write this differential equation, uxx plus ux whole square, this is equal to 0. What is the nature? Can you tell me what is this? Is it quasi-linear, linear, semi-linear, or non-linear? What is the nature of this? Hello? Hello? U multiplied by the second derivative of u with respect to x plus ux square equal to 0. The question is this: what kind of partial differential equation is this? Of course, the order is 2, so it's a second order. But is it linear? Hello? Hello? No response from the participants?
Sir, many of the participants are saying non-linear.
No, you see, I have talked about semi-linear, quasi-linear. They are definitely they are non-linear, but they are not fully non-linear. They are not fully non-linear, right? That's why it is called semi-linear, it is called quasi-linear, and I have stated the definition. Semi-linear means the coefficient of the highest order derivatives, they depend only on x and y, not on u and its derivatives. Quasi-linear, what is the definition? The coefficients of the highest order derivatives, they depend on u. So definitely, if it is second order, so now based on this, what can you say about this? Is it semi-linear? Definitely it is not. What is fully non-linear? You see, the fully non-linear would be this: ux square plus uy square, this is equal to 1. For example, equation like this. This is fully non-linear. First order, this is fully non-linear, right? But of course, these equations, I mean, they are all very special cases of a fully non-linear, right? This is here, the coefficients, they depend only on the unknown functions. Here, the coefficients, they depend only on the unknown functions, but the right-hand side, it depends on you. But here, had it been second order, then we could have allowed this A and B to depend on ux as well, right? Similarly here, so based on this, their answer is what it is it fully non-linear or quasi-linear or semi-linear? What is this? My question is this: what they are saying? Hello?
Sir? Yes, sir.
What is the answer from the participants? I just wanted to know whether they have understood the definition itself or not.
Okay.
All right, if there is...
the majority of the participants have said quasi-linear.
It is quasi-linear, very right. It is quasi-linear. Yes, because the highest order derivative appears linearly. Very correct, you see. The highest order derivative appears linearly, and therefore, according to this definition, it is quasi-linear. Now, if I write like this, ux plus uy, and it is multiplied by e to the power u plus sine of u, this is your uq plus x square u plus y. What is the, yes, classification? Yes, somebody tell me, what is the nature of this? Hello? Hello? Again it is quasi-linear. Why? Because the highest order derivatives appear linearly. Highest order derivatives, right? You look at the functions. They depend on x, y, and u. X and y are not there, but they are the functions of u. So definitely it is an example of a quasi-linear partial differential equation. What about this if I write 2x ux minus 2y uy is equal to u plus sine y? Can you, yes, somebody should be able to tell me what is the nature of this?
It is still quasi-linear.
This is linear because you see this coefficient, look at the coefficient. They are functions of x and y. Look at the right hand side, it depends linearly on u. So it is a linear one. It's a linear equation. Am I right? But of course, non-homogeneous. Linear, non-homogeneous. Right? Non-homogeneous means there is some term which neither depends on u nor its derivatives. So for example, this sine y, because of this it is non-homogeneous. All right, let us look at it. X ux plus x plus y into uy, this is equal to u square. What is the nature? As per classification, we will call it quasi-linear, non-linear, or semi-linear. Hello?
The semi-linear.
Why it is semi-linear? Very correct. It is semi-linear. The answer is correct. It is of this form. Yes, but semi is all right. If I write uy plus ux plus u triple x, third derivative. What is the nature of this? What you will call it? Hello?
Sir, it's quasi-linear.
You see, the highest order derivative appears linearly, that is true, but something more. What is that? What is the coefficient of the highest order derivative? Here the highest order derivative quasi-linear, they are the functions of x, y, and u. But if you look at the highest order derivative here, the coefficient is 1.
Yes.
Right? If the highest order derivative appears linearly, what did I say here? So definitely it is an example of a, yes, can you modify your answer?
It's linear.
Semi-linear, semi-linear, very
Yes,
right,
semi-linear.
semi-linear. All right, so this goes, the classification is like this. Now, all right, solution, so it's very clear. So by a solution means, if I'm looking for a function which satisfies the differential equation identically, right? A function which satisfies it identically, I will call it the solution, right? I will call it the solution. But it's very clear that if it is all right, let's consider only equation, simplest equation one can think of, dy u dy x plus c naught, or let me say that, all right, I think time, I'm going to replace y coordinate by time, dy u dy t plus c naught dy u dy x. This is equal to 0, right? And there is an initial condition that at t equal to 0, u is equal to u naught of x. This is a given function, a given smooth function, given smooth function. And here x is in R, and t, in fact, it is greater than 0. Right? U evolves according to this law, dy u dy t plus c naught dy u dy x. This is equal to 0. U is the unknown function. C naught is a constant which I can take to be positive without any loss of generality. C naught to be positive, and u naught is a given smooth function. You know that this is the simplest partial differential equation one can think of. Simplest. Nothing can be simple than this, right? The unknown function depends only on two independent variables, x and t. And such a differential equation is taught at the undergraduate level, right? Most of you may be knowing that what is the solution of it. Anybody can tell me what is the solution of this differential equation? Hello? Hello?
Yes, sir. Yes.
What is the solution? Can you tell me? It's a very well-known differential equation taught at the undergraduate level. In fact, this is one of the factors which appears if you think of a wave equation, you see, if you hold a string and which is fixed, okay, at the two ends, and if it is made to vibrate by pulling it into a certain shape, and if it is released from rest, it will vibrate from its main position of equilibrium, right? And the displacement at any x and t is governed by that equation. This is one of the factors, right? That is c square, this is utt, am I right? Transposing this to the left, what do you get? That is deva t minus deva x, or c times, or let's c naught, this operating on deva u deva x plus c naught deva u deva x. This is equal to 0. Is that right? I can factorize this operator. Second partial derivative with respect to t. This is second partial derivative with respect to x multiplied by c square. Transposing this to the left, I can write this differential equation in this form. So you can see here a solution of this is going to be a solution of this, right? So now can you tell me that what is the general form of the solution? Because it is taught at the undergraduate level. Anyway, we will derive it now. What is the methodology? The methodology is, it is called the method of characteristics. The method of characteristics. So what we do, we notice that there are certain curves in the xt plane. This is your xt plane, right? In the xt plane, there are certain curves, dx defined by this differential equation. Because you see, just by inspection, I can say that dx dt, if c naught is replaced by dx dt, then what is the operator? Deva t plus dx dt deva x. And what is this? It is nothing but the total derivative. So along these curves, the differential equation along dx dt is equal to c naught. The differential equation 1 becomes an ordinary differential equation. The partial differential equation 1 becomes an ordinary differential equation. What is that? Du dt, this is equal to 0. Is that right? Because c naught is dx dt. So this is, since u is a function of x and t, right? It's partial derivative with respect to t plus partial derivative with respect to x into dx dt is nothing but total derivative of u. So along these curves, the partial differential equation reduces to an ordinary differential equation, and it takes the form du dt equal to 0. What does it mean? This means that along these curves, these are the curves, c naught is a constant, so quickly I can write c naught t plus xi. Xi is an arbitrary constant. That is, if xt is any point through which it is a straight line, right? C naught is constant. If this line intersects the line t equal to 0, say at x is equal to xi, this point is x is equal to xi, right? At x is equal to xi, what is the information available here? From here it is clear that at x is equal to xi, in fact it is u is your u naught xi. Is that right? The value of u at t equal to 0. At t equal to 0 means on this line, it is u naught xi. What happens along this line? So this is called the characteristic, you see. This is called the characteristic of this differential equation. That is, it's a straight line in this case. Along this line, what happens? Along this line, u remains constant. Along this curve, which is a straight line, u is equal to constant. So what is u is equal? What is that constant? Whatever is the value available here, this information is transmitted into the region along the characteristic curves. Is that right? This is your u naught of xi. This is u naught xi. Is that okay? This is a partial differential equation of first order. I find that if there are certain curves in the xt plane given by this differential equation, such that along these curves which are described by this differential equation, the partial differential equation becomes an ordinary differential equation, and it gives me u is equal to constant. if u is equal, so along these curves, u is equal to constant means what? Xi. Now, if I eliminate xi from these two equations, what do we get? U is equal to u naught of x minus c naught t. Because xi, transposing the c naught t to the left, xi is your x minus c naught t. Substitute it here. And this is the solution of the partial differential equation, right? Number 1. Is it all right? This is called the method of characteristics, right? That is, whatever the information is available here, this information is transmitted into the region in which we are interested in finding out the solution, right? That is, u naught xi, u is equal to u naught xi, and xi is given by this. Xi element of these two will give us the required solution. So if u naught is a given smooth function, one can quickly see that it satisfies the differential equation. That is, what is your ux? Ux will be your u naught prime. Prime means derivative with respect to this argument function. Argument function is x minus c naught t, right? This is the argument function. Multiplied by what? Derivative with respect to, so it is only 1 because this is t, right? Derivative with respect to x, taking t as fixed. So ux is this expression. What is ut? Ut will be your u naught prime. What is prime? Prime means derivative with respect to the argument function. Chain rule, we are using chain, right? Ut will be your minus c naught. And from these two, yes, what do we get? If I multiply this equation by c naught and add, we get these two equations imply that ut plus c naught ux equal to 0. So you can see here that the equation is identically satisfied. Partial differential equation is identically satisfied, number 1. And number 2, at t equal to 0, now you can see here, at t equal to 0, u is equal to your u naught x. That is, the initial condition is also satisfied. And therefore, this is, in fact, is the unique solution of this partial differential equation. Is that right? So this is called the method of characteristics. Now you see this equation, although it is linear, but I tell you it is extremely important. It arises in a large number of physical processes. For example, if you think of suppose you have color or etc. or some pollutant is spilled in a stream which is moving from left to right with a constant speed, right? Then the evolution of u, this is the concentration of that pollutant, is governed by such an equation. It is called advection equation. And the solution, in fact, it is given by this result. This is extremely important. Not only that, you see, in PhD level courses, we discuss the solutions of the Euler's equations. Euler's equations of fluid dynamics. The Euler's equations of fluid dynamics, you see, when they are linearized, in fact, they admit a solution of this kind. They admit a solution of this kind. So anyway, we'll come to that later if the time permits. But this is what I wanted to explain, that how beautiful is this method, number 1, and how quickly it yields the result, right? So this is applicable, this is to be remembered, it is applicable to linear equations, semi-linear equations, quasi-linear equations, and in fact systems, because higher order equations can be expressed as first order systems. So it's a very powerful method, right? Now you can see in the physically what's happening here. You see physically what's happening, that this is your xt plane. This is your xt plane, and these are the characteristics. These are the characteristics, right? Emanating from each point of the real line, as we have seen here, a typical characteristic. If I allow psi to vary from minus infinity to plus infinity, right? If I allow this to vary on this real line, then I get a family of characteristics. And in fact, these characteristics, that's why you see I'm eliminating psi. So psi element of this, it gives me the required solution. That is union of all these characteristics. In fact, it yields the required solution. So if suppose this is your initial data, if this is the initial data, then at time, this is suppose at time t equal to 0, u is equal to u naught x. Suppose this is your u naught x, right? This is your u naught x. Then at time t is equal to t naught, suppose t is equal to 0, I say that t is equal to t1. At t is equal to t1, what happens? I can see here that this is the solution at time t equal to 0. The solution at any time t can be obtained just by displacing each point on the profile a distance c naught t towards right. It's very simple, c naught t towards right. So the solution in fact would be, in this case, it will be like this. U remains the same, u naught, right? U is equal to u naught x minus c. Only each point on the profile is displaced a distance c naught t. So here, this distance in fact is c naught t as a matter of fact, like this. So it goes on, right, like this. In other words, you see, I can show it like this. If this is your initial profile at time t equal to 0, profile at time t is equal to 1 will be obtained from here, but just by displacing each point on the profile a distance c naught t towards right, right? Here, so this point will shift to this point, right? This is your c naught t. Each point, this distance, right? C naught t. Solution at any time t1 can be obtained from t equal to 0 by displacing each point a distance c naught t1 towards right. Okay, very simple. And in this, that is, the initial profile is transmitted from one part of the medium to another part without any change in its shape, without any change in its, whatever the, yes, amplitude at each point. You see, you can see here, this remains the same. This remains the same. So there is no change in its shape, there is no change in its speed. The initial profile is transmitted from one part of the medium to another part without any change in its, say, at any two stations, you see, for example, which are at a distance d apart, the same signal would be recorded after a time lag of d by c naught. Because each point is translated, each point is moved a distance c naught t towards right, right? So it's very clear that in linear case, so this is the situation. If the differential equation is linear, homogeneous, right? Right-hand side is 0, linear, homogeneous, then it goes without any distortion. I mean, the profile propagates from one part of the medium to another part without any change in its shape. So it's very clear. If you look at the solution, this solution represents a wave phenomenon, right? If you look at the solution, the nature is that of a wave phenomenon. That is something which is transmitted from one part to another part without any change in its shape and speed. Right? This is what happens in sound waves. So, see, such a differential equation is said to be hyperbolic. Why it is called hyperbolic? You see, the basic idea underlying hyperbolicity is that Koshi problem is well posed. What is this? It's a Koshi problem. That is, we are interested in finding out the solution of this differential equation satisfying this initial data, right? This is Koshi problem. Koshi problem asks for determining a function which satisfies this differential equation identically and takes on some specified values on it, right? This is your Koshi problem. And if the problem is well posed means solution exists if it is unique and it depends continuously on the initial data, we say it is well posed. If it is well posed, right? So the hyperbolicity and well posedness, these two are important things, okay? So this is, now we will talk about what happens when it's not that simple. It's not that simple. You see, we have considered the most simple case. Nothing can be more simple than this. This is the simplest case. Okay. So, let's take a slightly somewhat, I think this is a first order x, y, u, ux. I just wrote b of x, y, u, uy, and this is your c, which is your x, y, u. So given a partial differential equation and some initial conditions, Let's say, for example, if I write that u at y is equal to say phi x, okay? Say y is equal to say y of x, some function of x. This is some function of x. This is the initial condition which is specified. Okay? So this is a Koshi problem, as a matter of fact, right? Problem is to find out the solution, right? We want to find out the solution of this partial differential equation satisfying this initial data. This is the initial condition. So it's a Koshi problem, right? Koshi problem. So how to proceed? The first step is to look for the characteristics. So now we will give a general definition. There, just by inspection, we noticed that C naught, if I look for certain curves, which are the solutions of dx dt is equal to C naught, then I can write it. I know the characteristics and I can write this in the characteristic form. But what is the definition, the general framework? So now look here, it's very clear that solution of this differential equation is going to be of the form u is equal to u of xy. Is that right? Hello? The solution of this differential equation is going to be of this form, right? And therefore, if I define this as some function, say x, y, u, just transposing this to the right-hand side, say u, x, y minus u. This is equal to 0. I mean, this function I define like this f. Is that right? Then what is your fx? Fx will be your ux, fy will be your uy, and fu will be your minus 1. Is that right? So grade f, this grade f is nothing but this vector ux, uy minus 1. Is that right? Looking at this partial differential equation, yes, it's very clear that its solution will be of this form, right? That is surface in the two-dimensional surface, okay? This is x by u space, surface in x by, right? U is equal to constant. U is equal to some function of x and y. This represents it.
Sorry to interrupt you, sir.
Yes.
Sir, some participants want to ask why the previous differential equation is hyperbolic.
Yes. So you see, there are physical reason. I think it is very clear, because when I say that day by u, day by t minus c naught day by u, day by x, right? Hello?
Yes, sir.
A solution of this is a solution of this. Is it all right? Hello?
Yes, sir.
So it is very clear that, I mean, from physical point of view, but the definition is this: an initial value problem, right, which involves a partial differential equation and initial condition, right, is said to be hyperbolic. That is, that partial differential equation is said to be hyperbolic if the Koshi problem has a unique solution, or you can say it has a unique solution, or rather, the solution is well posed, okay? That is, solution exists, it is unique, and depends continuously on the initial data. So this was an initial value problem, right? This was an initial value problem. If we can show that its solution exists, it is unique, and depends continuously on the initial data, means Koshi problem is well posed, because the function satisfies this identically and satisfies the initial condition as well. So what is the definition of hyperbolicity? The basic idea underlying hyperbolicity is this, that the Koshi problem is well posed. Is it clear? Hello?
Okay, sir. Thank you.
All right. So coming back to this, its solution has to be of this form. So you can see here, if I define a function like this, then the gradient of f, it has this coordinates. And as a result, I can write this differential equation as the dot product of two vectors, a, b, c, and this is your ux, uy, minus 1. Is that right? This differential equation can be written as the dot product of these two vectors. This is one vector having the components a, b, c in R3. What is R3 here? X by u space. This is x, this is y, and this is u, x by u space, R3. So this is a vector field in R3, and this is another vector in R3. Is that right? Is it okay? Dot product of two vectors, A dot B. If A has the components A1, A2, A3, and B has the components B1, B2, B3, then what is A dot B? Hello? If the vectors A and B have the components A1, A2, A3, and B1, B2, B3, what is A dot B?
It's simple.
That is mod A mod B cos theta.
In terms of components. You see, if A is a vector.
That is
Right.
That is simple A1, A2 plus B1, B2.
Right. So similarly here, you can see here that this is a vector and this is another vector. The dot product will be A1, A2, that is AUX plus BUY minus C equal to 0. Is that right?
Yes, sir. Yes, sir.
So what I again repeat, this is a given differential equation. These coefficients are known to us, A, B, C, they are given to us. So these A, B, C, these coefficients, they constitute this vector field. Is that right? A, B, C, this vector field. And UX, UY minus 1. Can somebody tell me what does it represent? UX, UY minus 1? Hello? Hello, what does it represent geometrically? It is nothing but gradient of I have just said. I have just mentioned it. It's very clear. This is a surface. Right? F is equal to 0 is a surface. F is equal to 0 is a surface. And its gradient, it has the components Ux, Uy minus 1. And what does it geometrically? What does it mean? It gives us the direction of the normal to the surface at any point. Is that right? So the dot product of these two vectors is 0. What is this vector? It is normal to the surface, to the solution surface. This vector is normal to the solution surface, and therefore this vector field must lie in the tangent plane at that point. Yes or no? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Yes. So a wonderful geometrical interpretation that a given partial differential equation, what does it represent? It represents, as a matter of, it's very clear from here. It can be described as determining a direction field in the R3. This is your direction field. This is the direction field which lies in the tangent plane to the solution surface, because this is normal. So this direction field lies in the tangent plane to the solution surface, right? So the differential equation may be regarded as determining a direction field. A, B, C are known to us, and therefore we know this direction field. Correct? What is the nature of this? This vector lies in the solution surface, as a matter of fact, because if you think of a point in space, x by u space, which starts from a given point in such a manner so that tangent at each point coincides with the instantaneous direction ABC at that point. Is that right? A, B, C, they are given functions. So we know how do they behave, you see, in the x by u space. If the point or think of a particle, if it moves in x by u space in such a manner so that starting from a given point, right? Starting from a given point which lies on that surface, what happens? What happens? The point, in fact, or you call the particle, will trace a curve in x by u space, right? And this curve will be referred to as characteristic curve of the partial differential equation. Yes or no? This is a geometrical picture. Is it clear? Starting from a point, right? Starting from a point which lies on the solution surface. Now, if the point moves in the x by u space in such a manner so that the tangent at each point coincides with this vector at that point, it moves in so that at each point it coincides with ABC at that point. Is that right? If the particle is moving or the point is moving in such a manner so that the tangent at each point coincides with the instantaneous direction of this vector field at that point, a space curve would be traced out. Yes or no? And this space curve is called the characteristic curve of the differential equation, and this will lie. This characteristic curve will lie in the solution surface. It will lie in the solution surface. Okay? If this is your, right? If it moves in such a way so that the tangent at each point coincides, right? Tangent at each point coincides with the direction of this vector field, then because this lies in the tangent plane, and therefore all these characteristic curves will lie in the solution surface. Is that right? And in fact, the union of all these characteristic curves will be nothing but this solution surface. So characteristic curves geometrically you can picturize that they generate the solution surface, they span the solution surface. Is that right? Hello? Is it okay?
Yes, sir.
All right. So, so this method, so now perhaps we can, what is the definition of characteristic curve now? The tangent at each point. So if I say that x is equal to x of s, y is equal to y of s, u is equal to u of s is a curve, right? It is a curve. Let me call it CH or simply C, right? S is the parameter along this curve, the locus of a point which depends only on one parameter, right? This represents a curve in space. Is that right? Hello? This is the parametric representation of a curve which is such that ds is equal to A, dy ds is equal to B, du ds is equal to C. What does it mean? It means that this point is moving in x by u space in such a manner so that tangent, because dx ds, dy ds, du ds, these are the components of the tangent vector to the curve at any point. Is that right? Hello? If r is the position vector of a point having the coordinates x, y, say u, right? And suppose x is a function of s, y is a function of s, u is a function of s, right? Then what is your drds? Hello? Drds will be your dx ds, dy by ds, du by ds. And what does it represent? A vector tangent to this curve, right? A vector tangent to this curve. And I have just mentioned that it is that curve such that tangent at each point coincides in the direction of this vector. So dx ds is A, dy by ds is B, du ds is C. These are called the characteristic curves of the differential equation. Is it all right? Hello?
Yes, sir.
So given a differential equation, quickly I can write the characteristic curves, right? And this is your, what does it represent? Initial condition. If you look at the initial condition, what does it represent? Hello? This is, you see, if you look at it, it is the intersection of two, hello?
Yes, sir. Yes, sir.
Yeah, so it's very clear. I can give a parametric representation to it, right? I can give a parametric representation. Suppose I take this as ux0 is equal to say u naught x. I take this curve to be the line t equal to 0. Very special case, okay, for the sake of simplicity. What is this? Y is equal to 0. Y is equal to 0 means here, all right, this is your y, so means x-axis. Y is equal to 0. Is that right? So I can give a parametric representation to it. I will call it, this is the initial condition, that is x is equal to xi, right? Y is equal to 0. And what is this? U is equal to u naught of xi. This is, xi is the parameter.
Sorry, sir, but screen is not visible.
Hello? Yeah, what's the point? Oh, sorry. Is it all right now?
Yes, sir.
All right. Okay. So this is the initial condition. So initial condition, this is the curve which is specified, right? It is a curve. This represents a curve. X is a function of xi, y is a function of xi, u is a function of xi. Of course, here it is 0. So definitely this represents a curve. Okay. So, hello. All right. So the thing is this, that the Koshi problem. Now, what is the way how to get the solution? how to get the solution surface. The solution of the Koshi problem. This is the Koshi problem. What is the way out? You think of this given curve, right? And allow these curves to emanate from this. Okay, this S is the parameter. S is the parameter along the characteristic curves, which emanate from these points. Xi is the parameter along gamma, and S is the parameter along characteristic curves. Is that right? This is your correct, right? This is a characteristic curve. CH. S is the parameter along this. Gamma is this initial curve. Initial curve is a fixed, right? So the Koshi problem, as I just said, it asks for determining a function which satisfies the differential equation identically and takes out some specified values on a given curve. This gamma is a given curve. Gamma is a given curve. All right, so you see only 3 minutes are left. I think we will continue next time. If there is any query in this, please let me know. This is very important. You see, this is the geometrical configuration, the geometrical picture of, how we are going to use the method of characteristics, correct? So I have explained that what the characteristics indicate. What do they mean? It is an integral surface, right? What do we mean by integral surface? When we say the integral surface of a vector field, means the surface is tangent to that vector field at every point. So it means the characteristics, they are the vector fields. Hello? The characteristic curves, they are the integral curves. What are the mathematical definition? What are the characteristics? They are the integral curves of the vector field. Right? At every point of this, the tangent at every point is parallel to this vector field. Dx is A, dy by ds is V, du ds is C. So these are the integral curves, and in fact the solution surface is the integral, right? That is the integral surface because it is tangent to the vector field at every point. So the best way to find the solution of a Koshi problem is to consider characteristic curves emanating from the different points of this given curve, right? From every point on gamma, right? Every point on this. Okay, and then the union of all these sweeping out a surface, and that is your solution surface. Perhaps the procedure I will discuss next time. So the time is up now, it's 5:59. Is there any query with regard to this? I would be happy if there is any question. Hello? Is there any question?
Yes, participants, you can ask your questions if you have any.
Sir, one of participants asked how solution surface is created geometrically. How solution surface is
Generated geometrically.
Yes, sir.
Yeah, that's right. I just mentioned that the best way is to think of characteristic curves emanating from this initial curve, and the union of all these characteristic curves, all these characteristic curves, they sweep the solution surface, right? They constitute the solution surface. This is the whole idea.
Thank you, sir.
So mathematically, how it happens, I will discuss tomorrow. Okay, that is union of all these characteristic curves. In fact, this is your solution surface. So we say that these characteristic curves, they span the solution surface. Just now, you see, did you notice that in the simplest example? In the simplest example, this is the characteristic, typical characteristic, right? For this dy u dy t plus c naught dy dy x. So what are the characteristics if I allow xi to vary from minus infinity to plus infinity? Yes, this is the, yeah, right. So these characteristics, as a matter of fact, they will generate, because what happens to u naught? U naught remains constant on each characteristic. So whatever the information is available here, it will propagate along this. Whatever the information is available here, it will propagate along this. So u is equal to u naught of x minus c naught t. That is union of all these. I have eliminated this xi, is the parameter, right? This is the variable xi, is varying from this to from every, right? So eliminating this, in fact, we are integrating all these characteristics to form a surface, and this is the mathematical equation or the form of the surface. U is equal to u naught of x minus ct, or u as a function of x and t.
Sir, there is one more question.
Yes.
Is there any difference in characteristics and characteristic curves?
Pardon?
Sir, is there any difference in characteristics and characteristic curves?
No, same thing. Sometimes you say characteristic curves or the characteristics of the differential equation, it is same thing, but it is better to call it a characteristic curve of the differential equation.
Okay, sir.
Right? In short, we say that when the characteristics intersect, what are these characteristics? They are the characteristic curves. Right? So in short, we say characteristics, but what are these characteristics? They are the characteristic curves of the differential equation. Is it all right? Hello?
Thank you, sir. And one question is, what is the classification of the Koshi problem if it is not well posed?
Again, repeat. What did you say?
What is the classification of the Koshi problem if it is not well posed?
No. We will not call it a hyperbolic. I mean, if the problem is not well posed, it is meaningless.
Okay, sir. Thank you.
Hyperbolicity means Cauchy problem is well posed for that partial differential equation.
Okay.
With respect to given initial condition, this is the meaning.
Sir, there is one more question.
Yes.
Yes, ma'am.
No, Parveen, you should read out.
Okay. Sir, there is one more question.
Yes.
Is there any notion to characterize first order PDs as parabolic or elliptic equation?
No. I just illustrated in this case because it is hyperbolic. I can factorize it. Take care of it. Yes, please take care of your mic. All right. So is it okay? Hello?
Yes, sir. Yes, sir.
So can we close this session?